welcome back to another StudyingWorks video. In this video, we are going to work through a previous FRQ for AP Chemistry, and I'm going to explain every single step as I go through it. Just so that the video doesn't go too long, I'm only going to be working through part of it, but if you want to keep up with this, make sure to subscribe so that you can catch up with when I upload the next parts of the FRQ. So let's get into the first part. So we are looking at FRQ number 1 today. So looking at this scenario, we have a student reacting 0.3 grams of methyl salicylate, which is C8H8O3, with a stoichiometric amount of a strong base. This product is then acidified to produce salicylic acid crystals, HC7H5O3. Okay. So for part A, we have for every 1 mole of C8H8O3, and we have our molar mass, reactant used, 1 mole of salicylic acid crystals, and again we have our molar mass, is produced. Calculate the maximum mass in grams of HC7H5O3 that could be produced in this reaction. So let's start with what we know. We know that we have 0.3 grams of our methyl salicylate. So to get to our salicylic acid, we have to convert using moles. So we'll have to get to moles of methyl salicylate. So we're going to convert to moles. So I'm going to just call it MC because it's methyl salicylate. Sorry, MS. And for 1 mole of methyl salicylate, we have 152.15 grams per mole. The grams are going to cancel out, and we're going to be at moles of methyl salicylate. Next, we're going to convert to, and we know the mole ratio is 1 to 1, so I'm just going to call our salicylic acid HA, and we know there's 1 MS. And then we know our mass, and we are left with 0.272 grams. Remember to always be conscious about your sig figs. So we had 3 sig figs here, 3 sig figs in our answer, because you never know when your AP grader is going to start paying attention to sig figs. So now let's go to part B. So for part B, we are given an experimental procedure to purify our salicylic acid crystals after the reaction is complete, and these crystals are filtered from the reaction mixture, rinsed with distilled water, and dried. So we're given some of the physical properties. We got our melting point, we have our solubility, which is basically how many grams can dissolve per liter at our 25 degrees Celsius in water, and we have our specific heat, which is 1.17 joules per grams degrees Celsius. So how many joules we need to raise 1 gram of our salicylic acid 1 degree Celsius. And we have our heat of fusion, which is the amount of heat required to make it into a solid or make it from a solid to liquid. So we see the student's experiment results in 87% yield of dry salicylic acid. The student suggests that some of the salicylic acid crystals dissolved in the distilled water during the rinsing step. Is this student's claim consistent with the calculated percent yield value? Okay, so this one is actually, it has nothing to do with the data we're given, so you want to ignore that, because really, right, it's just here to confuse you for this question. All this question is asking is, can salicylic acid dissolve in water? And the answer is yes, obviously, acids do dissociate in water, and so it is possible that some of it dissolved, leaving us with not 100% yield, because some of it dissolved and then we have our solid yield. So I'm not going to write that out, but I'm sure you understand Okay, we are now on part C. Given the physical properties in the table, calculate the quantity of heat that must be absorbed to increase the temperature of a 0.105 gram sample of dry salicylic acid crystals from 25 degrees Celsius to the melting point, which is 159 degrees Celsius, and melt our crystals completely. So, this is a thermochem question. So, first, if we remember from heating and cooling curves, we know that first we raise the temperature a little bit, phase change, raise the temperature, phase change, raise the temperature. So right now the first thing we're doing is raising the temperature. Then we are doing a phase change. So this is going to require us to calculate the heat required twice. So first we're going to use Q equals MCAT. Now, we don't know what our Q is, so we get Q equals, and we have 0.105 grams, and our specific heat from the previous problem is 1.17 joules per gram degree Celsius. And finally, our delta T is just going to be 159 minus 25, which is 134 degrees Celsius. So after that, we get Q equals 16.5 joules. Now this is where a lot of people are going to make a mistake. So now we've gone to that 159 degrees Celsius, so a lot of people will think, oh, the problem's done. But you have to read the question very carefully, because the last part says also you have to melt the crystals, and that also requires energy. So we are now going to use Q equals Ma. So this is the equation when we are having phase changes. So we are going to get Q equals 0.105 grams times our heat of fusion, which is the delta H we're going to be using. That is 27.1 kilojoules per mole. And here's one thing you're going to notice. Wait a second. Our denominator has moles, but we have grams here, meaning that our grams and our moles are not going to cancel out. So we're going to convert this 0.105 grams to moles. So we have our molar mass here, we got 1 mole, and again I'm going to just call it HA. Remember, on the AP test, do not use acronyms like I am. I'm just doing it for the purpose of making this whole process faster. Now, just to make things easier on myself, my previous answer was in joules, and this one is going to be in kilojoules, so I'm going to convert to joules, just so I can add them up in the end. And now we get this Q is equal to 20.6 joules. Now, to get the total energy, we are just going to add these two together, and you will get 37.1 joules. And that is the energy required to perform this entire process. Now, looking at this question, we have our methyl salicylate and salicylic acid shown below. We have their molecular structures, and this is a very common type of question where it will give you melting point or something of that sort, and you have to explain why one of them has a higher melting point than another. So let's look at possible reasons why. So the melting points are caused by intermolecular forces. The reason why they're different is because their intermolecular forces are different. So looking at this, we can see that our methyl salicylate can form hydrogen bonds. And we know that hydrogen bonds are formed with hydrogen bonding to F, O, or N. So we can see that right here. It's bonding to the oxygen here. But why is salicylic acids so much higher? It's because it has the opportunity to form more hydrogen bonds. And that is why the melting point is so much higher, because obviously more hydrogen bonds means stronger intermolecular forces, meaning it's going to be harder to break these bonds. So that is how you would explain this one. And now, for the next part, we are given a titration curve right here. Again, it's our salicylic acid with NaOH. So let's quickly mark this up just so we understand the meaning. So somewhere here is going to be our equivalence point. It's not exact, but it's just to get an idea of like around where, because you can see this spike right here in the titration curve. And since its equivalence point is at 10 milliliters, we know that at 5 milliliters, that's our halfway point, and that has a pH of about 3, and we can see our initial point right here. So now let's go to the next part. So using the information in the graph, estimate the pKa of HC7H5O3. So we know that at the halfway point, at halfway, we know that pKa equals the pH. And so when we check our graph again, we can see right here at our halfway point, we have the pH equals 3, so the pKa is going to be equal to 3. Now, when the pH of the titration mixture is 4, is there a higher concentration of weak acid, which is our salicylic acid, or its conjugate base? So, this one is a little more complicated. So, we know that when we are not at equivalence point and we have some acid, we have some conjugate base, we know that we are in the buffer region. And so that means that we know that at our halfway point, the amount of acid equals our conjugate base. So we know that when the pH is 3, our amount of acid equals our amount of conjugate base. So we know we start with only acid. Then, once we get to a pH of 3, we have acid, and at equivalence, we're going to have more conjugate base. So, as the reaction proceeds, the amount of acid is decreasing, the amount of conjugate base is increasing. So, we can see that the amount of acid we have is decreasing and the amount of conjugate base we have is increasing. And remember, because of equilibrium, it's not going to 0, it's just that it's decreasing or increasing. So, if our acid equals conjugate base at pH of 3, and our pH here is 4, meaning it's further this way, because we know equivalence is higher than a pH of 3, then that means that we must have more conjugate base because our reaction has proceeded further, our titration reaction. So that is how you would explain it. Now for part G, our student researches benzoic acid and finds it has similar properties to salicylic acid, and we are given a Ka. And then it says calculate pKa. Whenever you see P next to something, it just means negative log. So you take the negative log of our Ka. I'm not going to write it all out, but once you do so, and this is our Ka right here, you will get 4.20. Because remember, when you take the log of something, all of the sig figs here become decimals. Now we have arrived at the final part of the question, which is we are given again our salicylic acid titration curve, just to remind us, and it is telling us that we are performing a titration reaction with benzoic acid, and again we're performing it with NaOH. So it gives us our initial pH is 3.11, so let's just mark that somewhere here. And so now we know that because we have the same molarity and the same milliliters as our salicylic acid, we are going to be reaching equivalence at the same amount of milliliters because it's also going to be the same concentration of NaOH. So, because we know that equivalence is going to be at 10 milliliters, we can just estimate our titration curve. And we know that our pKa, which is at halfway, at about 5 milliliters, is equal to 4.2. So somewhere there. So now we just draw this, and then this isn't perfect because it's a little hard to draw with the computer, but the basic idea is that you should have a similar shape because they're both weak acids, and just make sure that you have a nice curve going through the points that I mentioned and finishing out as shown. So that is FRQ 1 in last year's AP Chemistry exam. I'm going to be trying to post these as often as possible, so make sure you subscribe so you don't miss the next one, and thanks for watching.